Hello and welcome to the first lecture series of Basics of Thyristor. So today we are going to learn some basic concepts and some basic terminologies for the industrial grade thyristors. So in this screen you are seeing a press pack thyristor. Okay, so these are basically the industry grade or the drive grade thyristors, and on the top you can see this is made by Infineon. Okay, and the code number or the model number of the thyristor is T2871N, and here are some key parameters of the thyristors. Reverse maximum peak reverse voltage is 8000 volts. ITAVM is the peak of the average current is 2620 amperes at a case temperature of 85 degrees. ITSM, it is the maximum surge current that can happen across the thyristor. VT naught is the forward voltage drop. RT is the on state resistance. So the net voltage drop will be 1.267 into the current flowing through the thyristor. Sorry, 1.267 plus the current flowing through the thyristor multiplied with RT, and RTHJC, this signifies how much the thyristor is able to dissipate its heat. Okay, and these are some mechanical parameters. Okay, let's see how to simulate a basic thyristor model in Plex. So this is the Plex standalone canvas that you are looking at, and to access the library we can access using Control plus L, and here we can search for thyristors. So if I search for thyristor, you can see there are few block sets or few FMUs, functional mockup unit, related to thyristors come up. So first is thyristor, second is thyristor with reverse recovery, third is the thyristor pair, and the fourth and fifth one are the thyristor rectifier and thyristor inverter. So we'll start with the basic model of the thyristor first, then we'll come into all this analysis or all these FMUs. Okay, so here if I drag and drop the thyristor, so this is a basic thyristor model, and if we double click it, we can see what is the forward voltage drop, what is the on state resistance, what is the initial conductivity, then the thermal description, and here it says thermal resistance, initial temperature, and some coder and association. Okay, so as we saw in the previous slide, we can get the VF and RON from the datasheet and the thermal resistance from the datasheet as well. Okay, so but for the initial analysis we can consider this as 0. So this is a basic thyristor model, and a thyristor is usually turned on by a positive gate signal, and the turning off of the thyristor depends on the level of current and the nature of the voltage across the anode and cathode. Okay, so to be clarified, this is the anode and this is the cathode part. Okay, so anode, if anode is more positive than cathode, then only the thyristor can conduct, or then only the current can pass through the thyristor unidirectionally, and if anode is less positive than cathode, that condition is called reverse bias condition. Then in that case thyristor will go into a blocked state and the current cannot pass from anode to cathode. Okay, so let's build a basic example model of a thyristor. So Okay, let's build a single phase half wave rectifier block. So I'll take a AC voltage source, connect it to the thyristor. Then I'll take a resistor. Sorry. Then I'll take a resistor and connect it to the another terminal of the thyristor and connect it back. So if I don't pulse it, okay, if I don't pulse it, can we get any voltage across the resistor? Let's see. Voltage, voltmeter, voltmeter, yeah, voltmeter, and then we can connect it across the load, and then we will take a scope to see the voltage, and then we'll run it. So to run it, you can go here, simulation start, or you can simply press Ctrl T. Okay. So as you see, there is no voltage across the thyristor, across the load, because the thyristor is blocking every voltage. And yeah, so now let's give it as a step command to turn the thyristor on. Okay, maybe I'll provide a on signal or the high signal to the thyristor at 0.02 seconds, and let's see the voltage. So as you can see, the thyristor is on at 0.02 seconds and the voltage continues in the positive half cycle. Okay, so let's analyze what is happening over here. So at 0.02 the thyristor starts conducting, and from 0.02 to 0.03 the thyristor stays in the conduction state. Okay, that's why we can see the positive cycle of the source voltage appear across the load. But from 0.3 to 0.4 we can see the thyristor goes into reverse bias mode, because the negative cycle of the source voltage is applied across the thyristor, and hence the load don't see any voltage. Okay, so if I zoom in a bit more, you can see the waveform is not smooth, or it is sampled at a very high sampling time. Okay, to reduce this effect or to make the waveform smoother, we can go to simulation parameters, and then we can choose the solver to stiff solver. Okay, so first to choose the solver to stiff solver, then we can reduce the maximum step size. Okay, let's first choose the solver to stiff solver, and then let's see. So if I do the simulation again, so the waveform is not smooth yet, so that's why we have to go back to the simulation parameters, and then let's make the step size as 1e minus 6. Okay, so now if I run the simulation and if I zoom in, you can see the waveform is far smoother. Okay, so these are few uh, points related to a simple thyristor circuit. Okay, now one more thing. As you see, we turn on this system at 0.02. Okay, and we keep on giving 1. Okay, let's say we'll remove the thyristor pulse at a particular time duration. Okay, so let's remove it at a particular time duration. Let's put a switch, signal switch, and then let's do some modification in this. So the signal switch says changeover switch. When the switch criteria is not met, the switch connects to the terminal indicated in the icon. Okay, and when the switch criteria is met, the switch will switch back to other terminal. Okay, so Let's say I'll put a constant as 0 and connect it to here. Okay, and then I'll take a clock. This is the simulation clock, and then a relational operator. And when the clock time is more than, let's say, 0.04 or 0.5, okay, then the the position of the switch will shift to the upper position, as it is said here. When the switch criteria is not met, the switch connects to the terminal indicated in the icon. Okay, so let's simulate it. Okay, so here uh, the when I remove the switch pulsing, the thyristor is off and we don't see a voltage afterwards. Okay, so the thing is, uh, we all know that thyristor is not a self commutating device. Okay, so now how the thyristor is off? So it is commutated due to the source voltage. Okay, and because the when you remove the pulse at 0.5 and the source voltage became reverse biased, and then after 0.5 there is no pulse across the thyristor. That's why it stays in the commutated state. Okay, so this completes the first lecture series of the basics of thyristor, and then we'll proceed towards the second lecture in the next video. So what we learned today is how to read the basic terminologies of a thyristor switch and how to simulate a basic thyristor model along with a voltage source. So tomorrow we'll be looking at what are the other parameters available in a thyristor datasheet and how do we integrate all those parameters into a fully fledged thyristor in a plex environment, and then we'll see whether these parameters that we provide into the thyristor matches with the datasheet or not. Okay, thank you for your viewing. Have a great day. Bye.